Cyril? Ouais. Okay, so the first thing I want to discuss is an obstruction to a full solution of KLS. So recall that we have seen that if x log concave satisfies some less than some constant for every s greater than some s naught, then Cp of x is less than square root s naught. And we have also seen that if x is isotropic, then S naught equals some constants log n square is okay. I mean that this holds for this S naught. Hence, the log n bound. But this also shows that KLS would follow from the following statement. For every S, for every X, isotropic log concave. And the obstruction is the following, that this cannot be true. Okay, here is the example. So take x equals x1 up to xn with xi iid, so independent coordinates, shows that xi plus 1 is exponential parameter, exponential variable with parameter 1. Okay. So the density of x1 is e to the minus x, indicator that x is larger than minus 1. And there should be a constant. Is it a plus 1 or minus 1? Plus 1. Whatever. Okay. And then the claim is the following. It's a proposition. Okay, first let me state a positive statement. What can I say about the covariant, the conditional covariance of this guy? I can say a bit, in this case, I can say a bit better than that. I know a bit better. I know that the covariance of x condition on x plus square root s g is less than some constant for every s less or equal. Non, c'est s grand. No, c'est the other way around. For every s larger than some sufficiently large constant multiple of log n. So it's slightly better. I can start from log n, not log n squared. However, I also know that the expected covariance of x condition on x plus square root sg is at least some small constant times s for every s less or equal than log n. No, here S0 for this in this case, S0 would be log n. It looks like it. Yeah, I'm not sure exactly how it behaves between log n and constant log n, but if you stop, if you yeah, so somehow, yeah, the behavior of this covariance can be pretty intricate. If you go up to log n, so it's roughly like s log n and c log n. Somehow at c log n, I know it's like a constant. So somehow, somewhere in between, it's somewhere in between log n and c log n, it decreases to here. That's the way it is. Yeah, I'm a bit confused because I'm more used to like the normalization t equals 1 over s, and then but I think this is the picture. Okay, and so what does this example? So recall that almost surely the covariance of x condition on x plus square root s g is less or equal than s time identity. So in particular, and this is true for every s. So remember this just because the conditional law has like is strictly log concave with parameter whatever, which gives you this. So the trivial bound, let me call this the trivial bound, expectation covariance x square root sg less than s can be essentially sharp on the time range zero s naught with s naught going to infinity. Okay, that's one point. So yeah, just so at time s naught equals log n, we have log n. So in particular, like my yeah, this shows that that's the thing that's on the very top up there cannot be true. Okay. There was another thing I wanted to say. Yeah, idiotic thing. Last remark. Of course, the Poincaré inequality has some tensorization property. So the Poincaré constant of x is just equal to the Poincaré constant of x1, does not depend on n. So x is not a counterexample to KLS, which so somehow the method of proof that we have for KLS has a gap even for product of exponentials. Yes?
Is there a relationship with the fact that when you take the example of the exponential, we know that the Poincaré constant is not rich? You have kind of potential spectrum inside.
Yes, that's a good point. No, I don't see any reason for that. You'll see, I'll say a few words about the proof. Sorry?
If you take e to the minus x to 1 plus alpha for alpha, which is between 0 and 1,
Yeah, probably. Except, yeah, it's not exactly the same tail. Okay, if I take x1 plus alpha, probably I would also have like some maybe a slightly smaller power of log, you see. So, I don't know. So this has to do with the fact with the tail. So let me say a few words about the proof. So, first, like just an obvious comment. Since everyone is independent, x1, x2, g1, gn are all independent. And yeah, well, this first n have the same law, and also this second. The conditional law of x condition on x plus square root s g is a product measure. So it's okay. It's a product measure of the same measure. Okay. So I don't know, like, yeah, bad notation. Okay, this. So in a sense, I only have to. Yeah. Okay, and let me continue. Tac. And also, yeah. So the covariance is diagonal with the IID coefficient, on the diagonal. So and the norm is just the maximum of these coefficients. So I just have to compute the expectation of the max of IID variable. So this is only I only need to look at the tail of this variable, one-dimensional variable, and then to do that. Okay, so we only need to understand the tail of x1 condition on x1 plus square root s g. Let me put like some lemma. Let g be standard Gaussian, real Gaussian on R. okay, I need to understand the conditional variance of G condition on G larger than some X. I just need like what's the order of magnitude of this function. So this is my very nice notation. That this is more or less, so it's more or less constant on R minus. And at plus infinity is like 1 over x squared. Okay? So positive part of x. Okay. No, x squared. Okay, the proof. So clearly, var gx is positive and continuous in x, and limit x to minus infinity equals 1. So okay, so it's it's by Braskamp or by whatever, it's also less than 1 everywhere. But actually, I don't really need that. But okay, so it's constant. So it's like between a constant, between two constants on R minus. Maybe there is some monotony. Not exactly sure. I don't really care actually. No, I don't. I only need to understand like behavior at infinity. So you can compute like the tail. So it only depends on the tail of the Gaussian, and you need to do like some asymptotic expansion for that. So it's a horrible computation because you need to go pretty far in the expansion to understand this. But here is a nice trick to save a bit of energy. Is that you can use what so G condition on G dot x is log concave in 1D. So the variance is more or less 1 over the L infinity norm of the density squared. F, okay, density. And the density then, this would be E minus Y, so Y, E minus Y squared over 2. Indicator that y is larger than x divided by integral e minus y squared dy from x to infinity. Okay, and so this tells you that so if x is positive, so this is if x is positive, this would be the largest. I mean, I want to like the infinity norm. So the point where this is largest is y equal x. Okay, and so like there is an inverse. So this is the other way around. E minus y squared over 2 dy divided by e minus x squared over 2 squared, and this is easily seen to be 1 over x. You know, this is the classical. Okay, so x squared. Okay, then you have some computations to do. I will spare some of the detail. So the conditional law of x1, so I'm only thinking in one dimension for now. Condition on x1 plus square root s g1 is some truncated Gaussian. And you do some algebraic manipulation, and you see that the covariance, so it's not the covariance, I'm in 1D, so the variance of x1 condition on x1 plus square root g1 is s times some function which I call v, which will be this function at point. So here I look at my notes. Hopefully they are correct. Square root s y sur assignation g. Square root s minus y1 divided by square root s plus g1. Okay, where? So v, first of all, v of x is this function. Sorry. And y1 is x1 plus 1. So it's x. Okay. And now you start to see, like you see what is going on. So maybe the lower bound for the variance. So observe that, what do I want to say? Hang on. Okay, so the probability that y1 is larger than s and g1 is larger than square is, well, zero will be good enough. These two are independent. Okay, so this is 1/2 for this guy, and this is exponential e minus s. Good, and when y1 bigger than s and g is positive, we have this thing here, square root s minus 1 plus g1 negative. And so the variance of x1 condition on x1 plus square root s g1 will be larger than, okay, so here in this function you will get something negative. So when the argument here is negative, the variance is order 1, okay? So this is order 1, and so this is order s. Okay. So the probability that the variance of x1 condition on x1 plus square root s g1 bigger than some constant times s is larger than half e minus s. And so the probability by the union bound then the covariance of x condition on x plus square root s g, no, not the union bound, sorry. Sorry? What is the... C'est bon? By, no, not the union bound, sorry. So this matrix, it has IID. It's just a diagonal matrix, okay? The coefficient on the diagonals, they are IID, okay? So the probability that the largest of them is larger than CS, yeah, you have to go the other way around for C. Well, you use independence, okay? So it's 1 minus this probability here to the n, right? I should have made the other one. The probability that it's less than CS is that the probability that they're all smaller than CS, so it's the product, okay? So I guess it's correct here. So I also assume that you see the number of minus here is even, so it's in the correct direction. Okay. So this should be 1 minus 1 plus E minus S over 2 to the n. And here I will just say that this is bigger than 1 minus 1 over n over 2 yeah, 1 over 2n to the n if S is yeah, here I'm confused, smaller than log n. Which is less than, I don't know, some constants. So by Markov, the expectation of the norm of this is larger than C double prime times S for S less than log n. Okay, the argument for the other bound is similar. Maybe I skip it. I don't know. Okay, for the upper bound. Okay, I'll do it in this thing. So probably I'll skip. Yeah, it's maybe a bit. I remember that for the upper bound, I need to just, I'll just prove you get something along this line. So you just prove something along this line. E minus, and so by the union bound, you will get.
You take upper bound in the same range for S.
Sorry?
The upper bound in the same. What is upper bound?
So I claim that. Yeah. Okay. I'll just give you like the one step. So I claim that this bound 1 minus CS for some C. I claim that this is always true, like for all values of S, and you get. So I'll put some dots here, and if you use also the fact that you have the covariance, blah blah blah, is less than S almost surely. So if you combine this with this, you will get the correct bound as long as you need S to kill this n. So you need S to be slightly larger than log n, and you see that it's okay. It's very tricky. Like if I am at log n, then the covariance explodes. But if I am at like some constant times log n, the covariance stays bounded. It's really like some sharp thing. And to prove this, So this is just union bound. So it's actually you just have to prove it in dimension 1, and then dimension 1 is like some similar argument to this, except that I will control by the fact that if those two are not too large, like comparable to the square root s, then I have v of square root s. Okay, if these two guys are comparable to square root s, then you see that this is v of square root s, so this is like 1 over s times s, so it's order 1. This is the idea, okay? Okay, now, so I think that's all for this, this example. No, I forgot to say something. Yeah, this was before the proof, like this was in the comments part. Okay, note. Okay, there's a gap between the theorem. So what I mean by the theorem is like the bound up to which I know that the covariance is bounded and my counterexample. Counterexample. So for Roy, I know it could be the case. So in my theorem, my theorem says if I take s larger than log n square, I'm in good shape. And the counterexample says I cannot go below log n, but it could be log n. Okay. It could be that E condition on x plus square root s g is O1 up to from s not equals log n on. And this would give square root log n for KLS. Okay. But somehow this seems to be like the limits you could reach with this method. Like if you want to go below square root log n, probably you need to do something else. Okay. Are there any questions on this? Yes?
So if you run this scheme for the exponential measure, you cannot prove it for the exponential measure?
Yeah, that's bad. Huh? Yeah. So somehow you should, yeah. If you run this scheme for the exponential measure, you get a square root log n bound for the Poincaré constant of the product of exponential, which is ridiculous because the Poincaré constant is just doesn't depend on n. I mean, it's just the Poincaré constant tensorizes. Like of a product is just the maximum of it. Yes. So.
And what do you think? Where is the point that you can improve at least for the exponential measure?
Yeah, this is a good point. I don't know. It's somehow you need to So last time I did this talk, like some guy told me like you need to like do some averaging, like to kill this counterexample or whatever. But not sure what he meant actually. But
so it means that you lose the product structure at some moment.
No, you never lose the product structure. No. You see from here, you never lose the product structure.
No, in the low proof, in the localization.
I never use product structure in localization.
Yes, so you lose it.
Okay, I'm not sure I understood, but all I'm saying is that if the conditional, the process like of law, the conditional law remains product for all time. So the stochastic localization respects the product structure.
Okay, so this,
Preserves. Okay, sorry.
does it mean that when you use the operator norm, this is the point where you use some?
Probably the estimates he gets with this method do not benefit from the product structure.
Yes. Yeah, so what do I use? I mean, when in the method of with this stochastic localization, I use the fact that I express my measure as a mixture of uniformly log concave stuff, and I have a good bound for the Poincaré constant of such a measure. But I mean, if my measure turns out to be a product measure, I don't see it during the proof. So okay, so anyways, that's life. Yeah, okay, I want, unless there are other questions, because I changed topic now. Yeah, I would say it's true, yes. I think it's true. I mean, I'll commit. I think it's true. But, no. I think KLS is true. Yes. No. This is some artifact of the. Okay. No, this I don't know, but. Now you could see a bit differently. So we also okay, Jim, maybe let me put it this way. I won't tell you why KLS is true because this yes, it's surprise. No. So see, we also remember that we also established that. This is correct, that is order 1 up until S not equals qu'est-ce que je voulais dire là? Cn log n. Approximately Cn log n. Where Cn is the KLS constant. Okay, so there was another version of the theorem I showed you about the covariance where I said, okay, I can do log n square, but I like by a similar argument, I can do Cn log n. Yeah, this is because, I always write with t, which is 1 over s. And then somehow Boas convinced me to put it in the other, but this is his fault. Yeah, this is his, it's because of Boas. Yeah, but it's more clumsy, like up until and from something on. Okay. Anyway. So if KLS is true, if Cn is order 1, then this is sharp. So somehow it seems likely that Cn is order 1, and that this analysis that we did here is like the best you could do. Sounds reasonable to me, I guess. But okay. More questions? No. Okay. Alors, okay. Further results. So related stuff. So let me talk a bit about concentration of measure. So it's another, if you want, isoperimetric type statement. So if mu is a probability measure, let me call alpha mu of R. So it's the concentration function. Sorry? Yeah, I convinced you? Yes. Concentration function. So the definition is this, alpha mu over. This is the largest 1 minus mu of SR, and the supremum over LS such that mu of S is 1/2. And this is the R neighborhood. Okay, you take a set S, you look at the enlargement, and you look at what's left, and you look at the worst case, and you call it the concentration function. So a bit like, so it's similar to isoperimetry, but somehow and the situation is a bit like in for the isoperimetric problem that I mentioned in the first lecture, that you only know the exact answer to this, like for the Gaussian measure or the uniform measure on a sphere or some very specific cases. And like on a general case, you're only interested in like some upper bound for this concentration and measure. And the link with Poincaré is that you have something that is called Herbst's argument, which is Poincaré implies exponential concentration. That is, for any measure mu, the concentration function is less than, I'll use this superb notation, exp minus C R divided by Cp of mu half. Okay. Okay, so Poincaré implies exponential concentration in a like a quantitative way, like the best constant you have in the exponential concentration is governed by the Poincaré constant. And again, so if you remember, like my first lecture, like which I doubt, for log concave you can reverse the hierarchy between often you can reverse between functional inequality, and this can be reversed for log concave. And again, this follows from Emmanuel-Millman's theorem. And let me just say one more word. This is because recall that the Poincaré constant of mu is more or less the largest variance of a one Lipschitz function, okay? Because you can somehow replace the L2 norm of the gradient by the L infinity norm, and you just pay a universal constant. But from concentration, it's like an exercise to see that if F is one Lipschitz, then the variance of F is less than maybe up to a constant integral 0 infinity r times alpha mu over dr. So if you have exponential concentration, you get, yeah, okay. So let me tell 0. So if you have exponential concentration, you'll get r times x, okay, so maybe a constant, x minus r divided by some constant, I don't know, cx. Let me call it like the exponential concentration constant. And this is more or less cx squared, okay? So far, so good. Quoi? Because it should be. Ah bah, je sais pas, on sait changer de variable là, donc non, attends, c'est... No, it's fine, it's fine. Okay, there is another notion of concentration which is called Gaussian concentration, like a stronger notion. Okay, we say okay, maybe before I move to concentration. So in particular, KLS is equivalent to alpha mu over for log concave isotropique. Okay. And our best estimate for KLS gives alpha mu over is less than E minus R divided by C. Let me get it right. Square root log n, right? Yes. Okay, what is exponential concentration? Okay, okay. So this we know. Okay, my point here is that I want to show you that I can do. We can actually do something a bit better than that. Okay. So I want to mention. So let me talk about what is Gaussian concentration. So I say mu satisfies Gaussian concentration if alpha mu over is less than x minus r square over cg. Okay. So instead of E minus r, you have E minus r square over cg. So that this I will call a Gaussian concentration constant. Okay, I don't write. So not every log concave measure satisfies this. Just think at the exponential measure. Okay. But again, like for Poincaré or many things, in the uniformly log concave case, we know that. Okay. So let me write a proposition. Oops. If mu is T uniformly log concave, then the Poincaré constant, no, the Gaussian concentration constant of mu is less or equal than 1 over T. Okay, some sort of proof. Proof sketch, very brief. This Boaz, we have not mentioned precopaline law. No? Okay, I don't know what we did this week, but okay. So there is something called precopaline law, which is like some functional form of Brun-Minkowski. And it tells you that if you take three functions, f of x, g of y, less than h, x plus y over 2, then you have the same comparison for the integral. So if you apply, so if mu e minus v dx with v, which is t uniformly convex, then you will have something along the line of v of x plus v of x plus y over 2 is less than v of x plus v of y divided by 2 minus, here I never remember, minus t over something, x minus y over square. Maybe 8, yeah, not 100% sure of this 8, but something along this line. And then you will apply, so fix S with mu of S, well, so let's take a set S and apply precopa to 1f, which is like 1s e minus v, g, which is exp theta distance from x to s e minus v, and h, which is e minus v, and probably you have to pay something, plus theta square times t times some appropriate constant. I don't know. T theta square, and then so you will get something along the lines of integral e theta distance from x to s d mu less than 1 over mu of s times e theta square. No, it should be better as t over some constant theta 3, and this implies Gaussian concentration. Okay, so T uniformly log concave measure have satisfied Gaussian concentration. That's sort of well known. And so here is maybe the theorem I want to prove. So, okay, this proof was the proof of the proposition, okay? Or a sketch of proof of the proposition, okay?
And the inequality just before,
the inequality that's before the proposition?
Yes.
Just above it, it's a definition. It's a definition of I say mu satisfies Gaussian concentration if. So that's the definition of CG. So what I mean, the proposition is if mu is T uniformly log concave, then its concentration functions satisfies this type of estimate. Okay, with CG equal order T. Did I got it wrong? No. No, it's okay. It's okay. And the proof, okay, you see, it's like it's some like you lose log you take advantage of uniform log concavity. I mean, it's you gain this x minus 1 minus y squared here, and it allows to like somehow when you apply precompo, you will okay you gain this and get some estimate here. Yeah, by the way, I should mention you can be a bit more precise than that. If you are T uniformly log concave, actually, I think it is true that the concentration function of mu is dominated by the concentration function of the corresponding Gaussian with no constant 1. This is called, it's a result by Bakri and Ledoux. I think it's true. And so you have an exact upper bound. But for my purpose, this is Bakri-Ledoux deep result. It would only matter for me at the level of the universal constant that I have here, which I don't care about. Yes?
You can also have the log-Sobolev constant involved?
It's related to log-Sobolev, but I think what I said is correct. Like.
It is correct if you use Caffarelli.
Ah, j'avais pas pensé à ça. Ouais. Ah yes, I'm stupid. Yeah, there is a. Well, I don't want to speak about Caffarelli. Ah yes, okay, I was thinking, but it was proved, maybe the Bakri-Ledoux result was prior, before Caffarelli. So, yeah, good point. J'avais pas pensé que, ah oui. Okay, what is the theorem? Suppose mu is log concave, isotropic. Then is less than some constant x minus some constant, the minimum or r square over log n square. Okay, so I can get Gaussian concentration for if I only assume that my measure is log concave. Okay, think of exponential. But I have some two-level concentration. Okay, it starts with like e minus r square over something that I pay here, log n square, and then when r starts to be larger than whatever log n square. Here it's log square. Yeah. There will be some command. I don't know how to. I don't know how to put log n here. Okay, I will say I know what you. Okay, so comments. One. Okay, once again, this is a statement. Where there is a log n square, so there's variant. So again, the same variant as where this is k-less constant. So that's first comment. To recall that Cn, okay, from the bounciness again implies x minus, well, alpha mu over less or equal than x minus c r over square root log n. Okay. Now, what is the comment? The comment is that this is not always better than that. I mean, it depends on the range. There are some range for which this is better than that. Okay. So I could write a better theorem where actually here I can put the maximum of this and this, but somehow for the things I want to tell you later, I don't need this improved version, okay? So I don't write. All I'm saying is that, which is better. On some weird range, on the range. And now I don't want to compute it, but some range log n alpha log n beta for alpha and beta well chosen. Ouais, je suis pas trop dans l'ordre. Okay, anyway. In particular, and this is probably why Boaz was not happy, is that if you apply, where is it? This thing here, with this function, you will only get a log n square bound for KLS rather than log n. But there is, it's not like my fault. It's just that to prove this estimate, I don't know how to implement the improved Lichner-Horowitz estimate in that. So to prove this estimate, I only use like this Bakry-Henri type result. So I don't know how to implement the improved Lichner-Horowitz in that. Okay. That's another result. That's another comment. A fourth comment which I should have made from the beginning. This is from Biesel, PhD thesis. Okay. So most of the material that I will present now is from Biesel. Okay. So. There are many things to say about this. Okay, a bit. Yeah, I mean like the credit. So this type of estimate, it's like it's reminiscent, or it was of a result. So before all this stochastic localization business from, so it was Millman, Guédon-Millman. Yeah, Millman, there is a convention that you should put the first letter from maybe 2011 or something like that. No. See? So the result was like, what was it? It was that mu of, okay, so it was some kind of estimate like that, but Okay, so some deviation estimate, but only for the Euclidean norm. So a much weaker estimate in the sense that like so here you have some logarithmic bound, and here it was like something polynomial. But you have the same time of double, and also here you see here it's a bound for the concentration function, so the deviation of any Lipschitz function, and here it's a bound for just the Euclidean norm. Okay, so it's more specific. And maybe let's just talk about, so this result, it implied what was at the time the best known bound, not for the KLS constant, but for the weaker one, the thin shell. Okay, it implied it was called sigma n is Boas-Stokes. So it's sort of trivial that sigma n is less than square root n, and to get in the first talk of Boas, he explained that to get central limit, you need something little o of square root n, and this estimate was sigma n is o of n to the 1/3, if I'm not mistaken. So which was at the time the best estimate for sigma n. And while I'm at it, it's okay. This is like inspired. So the work of Biesel is inspired by Livampala, 17, where they prove okay, the main result in the Livampala 17 was that the KLS constant is n to the 1/2. Okay, here I have bad notation because this 1/2 should be compared to 1/4. So okay, so then you can compare. So which also, so what I mean is that this also beats the n to the 2/3, even for the larger constant. But they also had this estimate that also, together with alpha mu over less than x minus c r minimum of r square over n to the 1/2. Okay, and here there is a slight, I don't know if you're following me, I've erased the theorem. You see, like, yeah, it's still here. So I will give you a break now, don't worry, but you see, Lee and Vampala, they prove the Poincaré constant is like square root n at most, and this deviation estimate without the log n, with the square root n here. Here, I have a log n. So somehow, you could ask, can you remove the log n from here? So no, you can't. The reason is, I mean, I don't know if you can, but in their analysis, there was a very complicated thing to remove the log n, because for their application, they needed to remove the log n, but it only works if you have some polynomial type estimate for the KLS constants. So now that we know some logarithmic thing, their argument doesn't work. So it doesn't help me remove this log. Maybe we make a short break, 10 minutes. What I will do is I will sketch the proof of this and give some application, maybe some further results, if I have time.